Let's look now at geometric sequences. And a geometric sequence is defined as a sequence in which the ratio of consecutive terms is constant. Here's an example of a geometric sequence: 4, 12, 36, 108, and we're going to explore this definition using this example. Well, first things first, what is T1? And remember, T1 refers to the first term. So we're looking at the first term, which in this case is 4. And so we would just say our T1 in this case is equal to 4. Well, because this is a geometric sequence, we're going to multiply. And we want to find out what can we multiply by to get from one term to the next. Now, you might be able to see this right away. If you can't, that's fine. But have a look here. 4 times what gives us 12? Well, it's pretty obvious. 4 times 3 is 12. Well, if we took 12 and we multiplied it by 3, we'd also get the next number, 36. And if you take 36 and you multiply it by 3, you're also going to get 108. So notice what we're doing each time here is we're actually multiplying each term by 3. 3, 3, 3, 3, working our way up. So what we're really multiplying by is 3. And this is what we call the common ratio, or the ratio that is common consecutively for these terms. So is this a geometric sequence? Well, because it has that common ratio of 3, you betcha it is geometric. And it would continue on that pattern if we wanted to find higher terms. Well, let's find some higher terms. We want to find the fifth term. So the fifth term would be the number right here, the number after 108. Well, if you remember back to what we just did, all we have to do to find the next term is take 108 and multiply by that number 3. And 108 multiplied by 3 will give us 324. So we could say T5 is equal to 324. And how did we do that? We just took our fourth term, 108, and multiplied it by the common ratio. Well, that's one way we did this. We could also have to find a term using just the first term, T1, and our value of R. We have to notice one thing about this. If we want to find our fifth term, we multiply by 3 here, multiply by 3 here, multiply by 3 here. There's 1, 2, 3 times we multiply by 3. Another time we multiply by 4. So if we took our first term of 4 and we multiplied it by 3 4 times, 1, 2, 3, 4, what we're going to end up with is that next number. Now, we don't really like to write it that way, so we would really say this is 4 times 3 to the 4, and we could find our fifth term like so, which becomes 4 times 81, which is 324. Now, if we do T5 like this, have a look at this number. This 4 is how many 3's we had, how many common ratios, and that got us the fifth term. Well, we're going to use that idea to now find the eighth term. We want to find the value of T8. And we want to find T8 using T1 and using our common ratio. Now the question though is, what exponent needs to go right here? Well, let's look at this example. To find term 5, we needed to put a 4 here. So to find term 8, all we need to do is put a 7 here. And then we know T1 is 4. we know the common ratio is 3, and we need to put this to the exponent 7, which would just be 8,748. Just keep multiplying our way up. So what do we notice when we compare the exponent to n? Well, when we did t8, we did t1 and r to the 7. If we do t5, we did t1 and r to the 4. And what you can probably tell, the exponent is always n minus 1. 1 less than the value of n. And we can use this information to write a general formula for this geometric sequence. And the general formula is trying to find the t to the n. The Tn for this sequence. We start with our first term, t1, and we're going to multiply it by r to the n minus 1. So our geometric sequence for this sequence is 4 times 3, let's put that in brackets, to the n minus 1. And that will allow us to find any term in this sequence. So we can use this information for any geometric sequence, because for any geometric sequence, the common ratio r can always be found by taking any term, except for the first, and dividing by the preceding term. So we could use a situation like this. The common ratio is just t to the n, whatever term you want, divided by its previous term, and that will always get you the common ratio. So let's test it out. Is this a geometric sequence? So we can find a common ratio and see if it is in fact common. Remember, we're just not going to use the first term. So if we take the second term, t2, divided by t1, which would be 4 divided by 2, we'll get 2. Now, if that's the same number each time we do that division, we have a geometric sequence. Well, t3 is 6 divided by t2 is 4, and we can probably see right away this is not equal to 2, it's equal to 3 over 2, and at that point we can stop because this is not a geometric sequence. What about this one? 4, 10, 25, 62.5. Well, let's test it out. 10 divided by 4 would be 5 over 2. And there's our first test, okay? So let's try t3, 25, divided by 10. Both those can divide by 5. We get 5 over 2. Alright, looks good so far. So let's try 62.5 divided by 25. And with just a little bit of calculation here, we'll actually see that this reduces down to 5 over 2. And because we get 5 over 2 each time, or 2.5, this indeed is a geometric sequence. Well, one way to represent a geometric sequence is using notation like this. It's the first term, and then the next term, in this case, this would be t2. Let's get the t a little better. Is the first term times the common ratio. Well, if we wanted to find the third term, we could take the first term, multiply by the common ratio twice, and again, you might think of it like this. It's t1 times r, and that pattern can continue. So we can think of it like this. T1 is obviously T1, T2 is the first term times R, T3 is the first term times R squared, notice that 2 and 3, T4 is the first term times R cubed, again 3 and 4, but look at this, we have a T1 here, a T1 here, T1 is consistently in each of these terms. This allows us to write a general term. The general term for a geometric sequence. And this general term, where n is a positive integer, is given by this formula. Tn equals T1 times R to the n minus 1. So we just need the first term and the common ratio and the value of n, and we can find any of the terms. Now that's if we have first term common ratio. We could also find any term by taking the previous term, the n minus 1 term, and just multiplying it by the common ratio. So depending on what we have, we can use either one of these equations. Now remember, the T1 is the first term, n is the number of terms, R is the common ratio, and if we wanted to write a general term, we would write it with the t to the n. So let's actually use this in a situation. And an example here, let's look at bacteria. Bacteria reproduce by splitting into two. Suppose we originally start with 3 bacteria present. Our question is, determine a general term that relates the number of bacteria to the doubling period of bacteria. What are we trying to find here? A general term. We want to find a Tn. That's what we're trying to find. And we're going to use the information that we have to find that Tn. Well, we are starting out here with our first term, and we start out with 3 bacteria. And we actually know the common ratio. The common ratio comes from that word right there, doubling. We are going to double the amount each time. And using T1 and R, we can use our equation T1 times R to the n minus 1. And this allows us to write a general term for this situation of Tn equal to 3. That's our original amount multiplied by 2 to the n minus 1. And there is our general term, and that'll allow us to find the number of bacteria given any n value. Well, let's use that formula then. We have our Tn equals 3 to the 2n minus 1. Let's put a bracket in there. And we want to find out how many bacteria will exist after 8 generations. So we're really trying to find the 8th term. And once we have that general equation, it really is that simple. Just put 8 in for n. So we'll get 3 times 2 to the 7. And as long as we do order of operations correctly, it's easy to get this number. We get 3 times 128, which ends up being 384. So we will have 384 bacteria after 8 generations.